for AMW ratios from 0.05 to 0.1. We also modified the compliance value over here, this one, and this is the standard test, standard geometry for 4-point bending in the base standard. To validate the numerical values with the experimental results, in the end, because we have to calculate the crack growth for the welded specimens, there are not 5 but more techniques to monitor crack, but these 5 are available in our laboratory. I decided to use strain gauges and potential drop for the validation of my data, as I have to perform testing in seawater conditions. So thermographic and DIC, digital image correlation, was not very successful because of diffraction and other, like after the corrosion chamber it gets a little blurry, so it cannot detect it. We haven't tried for the clip gauges. Okay, so the specimen is prepared like a notch is machined on the fusion line of the weld. We targeted the notch depth for 300 microns, but due to machining the tolerances, after scanning we found out that the initial notch depth is 311 microns. We also attached another instrumentation of potential drop. So here you see that at this point, this is a backface strain gauge. There is a crack over here, so these 2 points are measuring volts at the crack, and this is the reference voltage. And a direct current is passed throughout the specimen of 56 amperes. This is an experimental setup on which we performed a fatigue test. The stress range is the similar one which we used in the FEM models. The load ratio is 0.1, the maximum into the minimum, on the frequency of 10 Hz. The data is recorded throughout the test using data acquisition devices. This is the strain measurements that we received that we acquired from the experiment. Here the gauge length plays an important role. The smaller the gauge, it's difficult to place, but it gives quite strains in the very low regions. This initial value corresponds to the initial stress and initial notch sizes. Okay, so for the direct potential drop, we measured the current at the notch and at the reference voltage. We processed that in a ratio of V over VR. We then used the Johnson equation that is present in the standard. There were some instability issues in the start of the test in the DCPD, maybe due to sometimes it takes time to heating up, and also when the notch is small, there is a thermal influence. If the temperature changes, the conductance increases. It is measured in microvoltage, so they vary quite a lot. We normalize these voltage by dividing the initial voltages to account for the thermal influence. Okay, so this was the backface strain compliance that we can monitor the crack in the past, and this is an extended backface strain compliance that I present over here. And this is a transition in strain because we have developed now 2 equations, so it cannot be calculated with 1 equation. So we merge, and this is a transition point of both compliances. We plot the crack ratio of obtained from direct current potential drop on similar on to validate the both compliances. Here we see there is a slight difference in the crack length measurements of backface strain and the potential drop that's needed to be investigated with spectrography technique. As mentioned earlier in one of the presentations, the crack doesn't grow uniformly, so we think that in this there is a problem due to weld cement. The crack doesn't grow uniform. Okay, so this is a crack growth graph that I plotted with a schematic that is presented in the literature for the short crack propagation, like the regimes of initiation, propagation, short propagation, and the long crack. However, we have also developed a technique in which we can monitor a microstructural barrier, and we verified it using SEM, but I cannot present over here today because it's in review. Okay, so to conclude, we calibrated the equation for the back phase, and we developed an extended one, and the results were validated using a potential drop technique. Also, why I am using strain gauges? Actually, in seawater condition, strain gauge are the quite optimal choice to use because it can be protected easily. What we noticed with DCPD in the corrosive environment, that due to current conductance, the salt was accumulating on the pins of the DCPD, and the water is not anymore. The water was changing the salinity. So that's why we will be testing in seawater using only strain gauges. The parameters that we control using our hydraulic unit is pH, temperature, and dissolved oxygen. This is the future work that we will present in the paper. Thank you. If you have any questions.
Thank you very much. Any question in the audience? So, what will be the difficulty in testing in, with salt water from the sea?
The difficulty. Okay, one is like in thermographic cameras. If you place a thermographic camera in front of a chamber, it behaves with the infrared rays, and due to the reflection of arc-light, it gets the temperature from the back. Even if someone is passing, it changes the ranges over there. With clip gauges, they are quite sensitive and expensive equipments. We cannot place them in seawater. One of my colleagues put a membrane and attached a clip gauges on the notches, but then the membrane was protecting the notch and it was not purely immersed with the corrosion. So that's why we decided to go for strain gauges.
Okay, thank you. And which kind of temperature are you
we are using 12 centigrade of temperature because it's basically the partners are the Belgian offshore farms. So the temperature over there is average of 10 to 12. So we are testing on 10 to 12.
Okay. Yeah, there is a question there.
Just out of curiosity, what type of welding technique was it that was
it's
investigated?
FCAW 138 method. It's an arc weld, flux arc weld techniques. We didn't do it by ourselves, but smelters do it for us.
And then follow-up question. Do you consider the effects of residual stress on that weld in
okay.
or not?
That is out of the scope of this project also, because residual stress is not an easy thing.
Yeah, fair enough.
Yeah. So also, but we want to conclude something for the residual stress, because that's the main question if you talk about weld. While we were measuring the strain data, we don't see any fluctuation of residual stresses. So we assume that due to machining, milling, and we also do the electropolishing on the notch, the residual stresses might go away. But I'm not saying that scientifically.
Okay.
Okay, you're done.